Okay, so in this second example, what we're trying to do is we're trying to analyze some prices with respect to crude oil. And what we're trying to do is we're trying to work out which type of function gives the best fit for this series of prices. So let's actually, this was pre-done. So let's actually do this from scratch. So what we want to do first is we want to draw a line graph. So we basically have a bunch of months and then the crude oil prices per month. It would actually be very interesting to see the current graph as crude oil is rapidly rising at the moment. So let's just insert. And we basically just want a line chart. So there we go. The default options actually give us the chart, and we'll just say crude oil over time. And then we'll just say price per barrel. Or just price will do. And then we'll have the date. Now, what we're going to do now is I'm going to make this a little bit smaller. And I'm going to kind of create some copies of it. So I'm going to just Control C, Control V, and I'm going to do 1, 2, 3, 4, 5, maybe 6. There we go. And I'm going to fit a different function to each of these. So let's click the data series and then right click, as we did in the previous example, add trend line. And we're going to add a linear trend line. And we're going to just paste the equation and the display r squared on the trend line. And let's make it red. No dash, so we can see it a little bit better. And then we can see the equation here. This is the general linear regression equation. We can see it doesn't fit particularly well, as you know, as we don't really expect it to. And the fact is, this sort of data generally it's difficult to fit trends with anyway. We'd be better off with some of the, sorry, long-term trends. We'd be better off with some of the time series techniques that we're doing next week. But again, this is just kind of a simple example modeling the price over time. Okay, so we have the linear example. Now we're going to fit the polynomial second order. So let's just right click on this, add trend line, polynomial order 2. And again, let's do red and no dash types. And you see this fits a little bit better. Again, let's display the equation and the r squared. You see the r squared is now 0.9. And let's just do the polynomial of order 3. In fact, I might have been better getting the trend line and then copying and pasting to avoid me having doing this every time. And you see it fits it even better this time. Display the r squared on the chart and the equation. You say we have a third degree polynomial, 0.9282. I'll just do the remainder, and then I'll talk a little bit more about fitting functions in general. So the next one we're going to do, so we have our 3 polynomial ones here. I'm going to do an exponential function. This doesn't seem particularly exponential to me, but let's add a trend line with an exponential function and display the equation on the chart and r squared. And again, we're going to make it red with a line. And you see, because it's not exponential, it kind of almost just ends up almost as a linear graph with a slight curve. You see, we have this, we're not really, I'd have to make the font bigger to make this bigger, but you can see that we have this very small exponential term, but we have, the base term of 50, which is this very gentle exponential. I think the next one was logarithmic. And you see this just does the opposite direction. So this is completely useless. And it's got a very low r squared. So that's good. That's not a very good fit at all. And the next is going to be just a general kind of power function. It's kind of quite similar to the exponential. So add trend line, power. And again, 0.4345, a pretty poor fit. Let's just try this up here. And again, let's make this one a little bit bigger. It's got an exponential. There we go. So what we've done is we've fit 6 functions here. Now you see that these guys here, they each have we've kind of fit 2 variables, 2 parameters in each of these 2 numbers, but they have pretty poor r squared. So I think I'm just going to get rid of this one, and possibly this one, though it is a little bit better than the linear. And we can see that the kind of the polynomial, if we have degree 1 polynomial here, a linear function, we have r squared of 0.6596, degree 2 0.9059, and degree 3 0.9282. But the thing is, you have to be really careful here, because we're kind of fitting existing trend, and we're potentially overfitting the existing trend. It's not necessary that the future series will kind of continue on like this. So there are ways of we could maybe do some out of sample validation, which I talked about on the initial video. The book here just says, just be aware that, you can overfit if you fit too many parameters, so just use your common sense. So it may be that this second one is a nice compromise, in that we've gone up from r squared of 0.65 to 0.9, and the additional parameter doesn't really give us a huge additional amount extra fit than before. But just be really wary. On standard regression, we can fit our adjusted r squared. I'll talk about that in a different video. And also, I think one of the homeworks mentioned, hey, if you add an extra parameter and r squared increases over by 0.05, this makes it worthwhile. But just be very wary about having too complex fitting of your data if you want to think about doing any future prediction from the models you create. So I'm a little bit more cynical about this than the book, but in these videos I'm recreating the book examples. This was example 8.2 from the textbook.